Some functions we run into in applications are a little bit too complicated to be described by a simple formula for a function like a polynomial function or a rational function. Sometimes we need to piece together several different simple formulas to come up with an adequate description. For example, imagine we're trying to describe the cost of mailing a package, and we're told the cost is $6.95 if the package weighs up to 2 pounds, and then if it weighs more than that, we add $3.95 for each additional pound. And I want to write down a function for the cost where we're expressing it in terms of how many pounds our package weighs. So if it weighs less than 2 pounds, the value of our function, the cost function, should just be $6.95. But if it weighs more than 2 pounds, then we have to take the number of additional pounds. So if it weighs X pounds, then there are X minus 2 additional pounds. Multiply that by the per pound cost of $3.95, and then add that to the base price of $6.95. So we have two different formulas here depending on whether X is less than 2 or greater than 2. And so we can express all that in this notation. The idea is we have two different formulas depending on what we're plugging in for X. If X is less than or equal to 2, we use this formula. And if it's greater than 2, we use a different formula. And this notation tells us how to do that, how to evaluate the function. Someone reading this will know to check on the right side whatever they're plugging in and decide which row to use based on these conditions. And once they decide which row to use, then they can use the corresponding formula. So for example, if they want to evaluate the cost of mailing something that weighs 5 pounds, they'll look over here and say, well, I'm plugging in an X that's bigger than 2, so I have to use the bottom row, which means I have to use this formula. So this is called piecewise function notation, and you run into this a lot when you're trying to describe complicated functions like the one in this application. Notice how we've got a different row for each formula. Each row tells us what X values it gets used for, and the whole thing is grouped together with this French brace. That's important in order to keep your work lined up and easy for others to read. So let's look at an example where we're calculating the values of a function that's defined in this way, defined as a piecewise formula. Here our function c of x has one formula if x is less than 2, a different formula if x is greater than or equal to 2 and less than or equal to 4, and yet a third formula if x is greater than 4. So just as an exercise, let's complete an input-output table for the x values 0, 1, 2, 3, 4, 5, and 6. So to start our table, imagine we're plugging in 0. What we do is we look at each row and decide which one to use based on the descriptions. We can see that if we're plugging in 0, I want to use the first row because 0 is less than 2. So that means I plug a 0 into this formula. 0 squared plus 1 is 1. That's where this comes from. Now let's look at the next value. I want to figure out what happens if I plug in a 1. 1 is still less than 2, so I still use the first row. Plug a 1 in here. 1 squared plus 1 is 2. What if I plug in a 2? Well, 2 is not less than 2. I cannot use this row because 2 does not satisfy the description. 2 is not less than 2. 2 is actually equal to 2, so I really want to use the second row. This is x values that are greater than or equal to 2. Using the second row, plugging a 2 in here, I get 4 minus 3, which is 1. If I plug in a 3, I use the second row because 3 is between 2 and 4. 2 times 3 is 6, minus 3 is 3. Plugging in a 4, I still use the second row. 2 times 4 is 8, minus 3 is 5. Plugging in a 5, now I've moved down to the bottom row because I'm plugging in an x value that's bigger than 5. And the output is just 4. And the same thing happens when I plug in a 6. I use the bottom row, and the output is